Have you ever stopped to wonder what makes a baseball fly or why you lurch forward when a bus suddenly hits the brakes? Well, turns out there's a set of invisible rules that govern pretty much all movement around us. These rules were written down over 300 years ago by Sir Isaac Newton, and today we're going to unpack the three big ones that explain, well, basically everything. But first, let's start with a little puzzle. Look at this. Someone yanks a hoop away and a golf tee drops perfectly into a bottle. How do they do that? It looks like a magic trick, right? I promise you, it's not. And by the time we're done here, you'll know exactly how to pull it off yourself. All right, to solve this puzzle, we first need to understand the forces at play. So let's look at our golf tee in two very different situations. First, when it's just sitting there, and second, when it's falling. And it all comes down to one simple idea: balance. See, when the tee is at rest on the hoop, the forces are perfectly balanced. Gravity is pulling it down, sure, but the hoop is pushing up with the exact same amount of force. They cancel each other out. But the second that hoop is gone, gravity becomes an unbalanced force. There's nothing pushing back anymore. And that changes everything. This idea of balanced versus unbalanced forces is the key to all of this. This brings us straight to our first big clue, Newton's first law of motion. You can kind of think of this as the leave it alone law. It tells us what things do when you're not messing with them. So here it is, the official definition. An object that's not moving will just keep not moving, and an object that is moving will keep moving at the same speed and in the same direction unless, and this is the important part, an outside unbalanced force shows up. Honestly, the easiest way to think about this is to call it the law of laziness. Objects are just lazy. They want to keep doing whatever it is they're already doing, whether that's sitting still on a table or flying through space. They will not change what they're doing unless something forces them to. Now, this laziness has a proper science name, inertia. It's just the tendency for an object to resist any change in its motion. Our golf tee has inertia. It wants to stay put. It's the same reason that if you put your phone on the dashboard of your car and take a sharp turn, the phone tries to keep going straight. It's not magic, it's just inertia. Let's make this even more personal. Picture this. You're in a bumper car, and bam, you hit another car and come to a dead stop. The car stops, but what about you? Well, your body, because of inertia, wants to keep right on moving forward. You fly forward until your seatbelt, that's the unbalanced force, catches you. See? You've experienced Newton's first law your whole life. Okay, so if the first law is about what happens when we leave things alone, the second law is all about what happens when we don't. This is the law that connects force, pushing and pulling, to an actual change in motion. So the law says that an object's acceleration, which is just a fancy word for how quickly it speeds up, slows down, or changes direction, depends on two things: how much stuff it's made of, its mass, and the total force you're hitting it with. And this whole idea is wrapped up in one of the most famous equations in all of science, F equals m times a. And here is a really crucial connection. An object's mass is basically just a measurement of its inertia. The more mass something has, the more inertia it has. That just means it's a lot harder to get it to change what it's doing. I mean, think about it. You've been there, right? Pushing a shopping cart. If it's empty, it's easy to get it going. But if it's loaded down with groceries, you have to push way harder to get it to speed up at the same rate. More mass means you need more force for the same acceleration. It's that simple, but it's so powerful. And the great thing about F equals ma is how flexible it is. You can just rearrange it to find any one of those three things: force, mass, or acceleration, as long as you know the other two. It's like the ultimate user manual for how things move. So, we've covered what happens when objects are left alone, and we've covered what happens when we apply a force to them. But what about when two objects actually interact with each other? Well, that's where the last piece of our puzzle comes in, Newton's third law. Now, this is probably the one you've heard before. It's usually shortened to, for every action, there is an equal and opposite reaction. What it really means is that forces never exist on their own. They always come in pairs. Look at a swimmer pushing off the wall of a pool. The action is her feet pushing backward on the wall, but the wall doesn't just sit there. It reacts by pushing forward on her feet with the exact same amount of force. And it's that reaction force that actually shoots her across the pool. She pushes the wall pushes her. It's a pair. A really simple way to remember this is you can't touch something without it touching you back. I mean, think about it. If you accidentally bang your hand on a table, the table hits your hand back with the very same force. And that's why it hurts. Okay, we now have all three of Newton's laws in our toolkit. So let's put them to work and see how they all come together in a real-world scenario. Let's go to the ballpark. First, let's just look at the stats. As you can see, a softball is quite a bit heavier than a baseball. And this difference in mass? This is where things get really interesting. So imagine a batter swings a bat with the exact same amount of force, 2 times. First, they hit a baseball, then they hit a softball. Which one's going to go farther? It's the baseball every time. And the reason is Newton's second law. Remember, acceleration equals force divided by mass. Since the force from the bat is the same, the ball with less mass, the baseball, gets a way bigger acceleration. It just flies off the bat faster. All right, the moment of truth has arrived. We've talked about inertia, we've talked about force and mass, and we've talked about action-reaction pairs. Now, it's time to bring it all home and finally solve that mystery from the beginning. Let's break it down. 1. To start, the T is at rest. The forces are balanced. Gravity pulls down, the hoop pushes up. Everything's stable. 2. The hoop gets yanked away sideways. But Newton's first law says the T has inertia. It resists that sideways motion. It wants to stay put, so for a split second, it literally just hangs in the air. 3. Now the hoop is gone, which means there's no upward force anymore. Gravity is now a completely unbalanced force. And 4. What happens with an unbalanced force? Newton's second law tells us it causes acceleration. Gravity takes over and accelerates the T straight down, right into the bottle. See? Not magic at all. It's just physics. And there you have it. 3 simple, elegant laws that explain the motion of everything from giant planets orbiting the sun to penguins sliding across the ice. These rules are happening all around you all the time. So the only question left is, now that you know what to look for, where are you going to see them next?